Some common reductions in acidic solutions include nitrate, permanganate, and dichromate. And unfortunately, the only thing to do is just to sit down and memorize these. We did look at nitrate just above. Um, these nitrate, permanganate, and dichromate really want to gain electrons because they have atoms that are higher or more positive oxidation states than usual. And when they gain electrons, the oxidation numbers of these atoms will drop to more appropriate levels. For example, nitrogen is going to drop from +5 to +2. We know that because it's a group 5A, it would like to go as low as -3. Manganese drops from +7 to +2 because +2 is its most common charge for an ion. Chromium drops from +6 to +3. +3 is its most common charge as an ion. Another example would be the oxidation of sulfite. The oxidation number of sulfur in sulfite is +4 and in sulfate is +6. So that's going to create an increase in oxidation number. Oxidation of hydrogen peroxide. Hydrogen is going to go from a -1 in H2O2, hydrogen peroxide, to 0 in oxygen gas. Now here we have the oxalate ion. This is a substance that has a lower or a less positive oxidation state than usual. So in oxalate, carbon has an oxidation number of +3. Carbon is in group 4A, so it would rather have an oxidation number of +4. So it's going to oxidize or lose electrons to raise its oxidation state. So it goes from the oxalate ion to carbon dioxide. Some nonmetals are going to raise their oxidation states by bonding with like elements. This is what happens when hydrochloric acid combines with a species that's easily reduced. The chloride ion goes from a -1 charge into a 0 charge with chlorine gas. So what do you do if you have a choice of two species that can be oxidized? When compounds that have P or D block metals and nonmetals with less positive than usual oxidation states, then the metal is going to be oxidized. So when we have 10,2 chloride here, the 10 is going to be oxidized to 10,4 as opposed to the chlorine being oxidized. So here's our example. We have an acidic solution that has 10,2 chloride mixed with a solution of potassium permanganate. So we're going to write the balanced net ionic equation for this. So what are the reactants going to be? Now remember that potassium is a group 1 metal, so it's going to be soluble in everything. We know it's going to be a spectator. The permanganate ion is going to oxidize metals. So in this case, it's got to oxidize 10,2 because it's the only metal available. The chloride must also be a spectator ion because the 10,2 is a metal and it's going to be the preferred reducing agent. So our products here are going to be our permanganate ion and our 10,2 ion. So what are the products going to be? We're going to get our manganese +2 ion and our 10,4 ion. So we need to balance using our special procedure, our half reactions. So if the question states the solution is acidic or acidified, you have to balance it using this procedure. Now let's talk about the products real quick. You know that permanganate is reduced to manganese +2 in acidic solutions because you just had to sit down and memorize it. You also know that it oxidizes 10,2, which has to lose 2 electrons to become 10,4. Again, this is why you just need to memorize the possible oxidation states of metal ions. For example, 10 can be +2 or +4. So for balancing, we're left with oxygen atoms on only one side and charges that don't balance. So we have to use our half reaction method. So let's start with step number 1. Let's do the reduction half reaction. Our reduction half reaction is our permanganate going to manganese +2. So we're going to balance everything except for O and H. Well, manganese is already balanced. There's one of each. Now we have to balance for oxygen by adding water. So we're going to add waters to our product side because that's where we need our oxygens. And because we have 4 here, we're going to need to have 4 waters. Now we have to balance hydrogen by adding our H pluses. And because we have 8 H's over here, we've got to add 8 H pluses. Now where are our electrons going to be added so that we balance our charge? We add our electrons here, and there's 5 of them because we have a +8 and a -1, so +7. We have a +2 here, so that means we need 5 electrons so that our charges balance. Now we look at our oxidation half reaction. So that's our 10-2 going to 10-4. Balance everything except O and H. All we have are 10 here. Then step number 3 is to balance O by adding H2O. We don't have any O's. Step number 4 is to balance H by adding H pluses. Don't have any H's. So where are we going to add the electrons here? So our electrons get added to the products to balance out our charges. Now step number 6 is to cross multiply. So let's look at both of our half reactions here. Now what do we need to multiply both of our reactions by? We have 5 in our reduction, 5 electrons, and we have 2 in our oxidation. So we need to have 10 electrons for them to cancel out. So we're going to multiply our reduction reaction by 2 and our oxidation reaction by 5. So here's when we multiply all of those out, and then so that will allow them to cancel. So the next step is to add our 2 half reactions. Alright, now both sides have a charge of +24 and both sides have the same number of each type of atoms. You always have to double check this at the end. If the charges in the atoms do not balance, then we did something wrong. But all of our charges and all of our atoms add up, and this is our balanced redox reaction. Now the half reaction method can be used for other redox reactions. Now if there's no H2O or H plus in the balanced chemical equation, they're going to cancel. But if water or H plus may appear in the half reactions. So you could be given a redox reaction and be asked to write the oxidation or reduction half reaction. So for example, write the balanced oxidation half reaction for the decomposition of hydrogen peroxide. So here's our equation: hydrogen peroxide going to water and oxygen gas. So step number 1 is our oxidation half reaction. Step number 2, we're going to balance all atoms except for O and H. Well, that's all we have. So step number 3, we're going to balance for O's by adding waters. Alright, our oxygen atoms are already balanced here. Now why are we not putting water in this equation? Because it's a liquid, remember, and it's not going to go in there. So oxygen atoms are already balanced. We have to balance our H's by adding H pluses. So we do need 2 H pluses on our product side. Now where are we going to put our electrons? They're going to need to go in our product side so that our charges cancel. And then that is our half reaction. That's the only thing that we have to do.